All right. So next we have Siddharth Bhandari from TIFR, and he'll be talking about ideal-theoretic explanation of capacity achieving codes. Okay.
Yeah. Thanks for the introduction. So in this talk, I'm going to describe recent work that I've done with Prahlad, Mrinal, and Madhu, and we are going to sort of give an unifying explanation of codes which achieve the so-called list decoding capacity. So let's begin. And I mean, I guess most of us know what a code, etc., is, but nonetheless, to just do a quick recap. So a code for us is just going to be a collection of points in sigma to the n, where the alphabet is sigma and the block length is n. The rate of the code is this thing which we all know. It's the amount of information you can send in bits per bit. So that is just the log of the size of the subset by n. And the distance of the code is the minimum distance between any two strings in the code. So the minimum Hamming distance, that is, you look at the coordinates where x and y differ, and the number of such coordinates is the Hamming distance between x and y. And sometimes I'll use the symbol little delta to refer to the fractional distance of the code. So in general, we will only be dealing with linear codes. So these are codes which further enjoy the property of being a linear space over the alphabet. So in this case, the alphabet is a finite field fq, and the collection of points that we are interested in is a vector space over fq of dimension k. And because of linearity, it's sort of not difficult to see that the distance of the code, which was earlier defined as a property where you have to go over all pairs of strings, now you can sort of fix y to be the all zero string. So all you need to find is the lowest weight non-zero vector, that is the distance of the code. And there are two equivalent ways of describing a linear code. One is as the image of a generator matrix, and the other is as a kernel of a parity check matrix. And these are also fairly simple definitions, and let me proceed anyways. So what is one of the central problems in decoding codes, that is of unique decoding. So suppose we have our code script C, and we are given a word W in sigma to the n. So our code script C, remember, it resides in sigma to the n, and we want to find the closest code word C to W where C is in script C. So if it is promised to us that the distance between W and C, the code word that we want to find, is less than delta by 2 times n, delta was the fractional distance of the code, then we can be at least assured of the fact that such a C is unique. That is, there is only one C which is within a ball of radius delta n by 2 around W. And again, the ball is in the Hamming matrix. So it should be clear that this C is unique, because if there are two such C's, C and C prime, then the distance between C and C prime will fall below little delta, or delta n, sorry, in this case I've forgotten an n, and which is a contradiction. And of course, there is an algorithmic counterpart to this, that given a description of script C, can we find this little c efficiently? But we'll come back to this question. So now I'll define the concept of list decoding, which is what the talk is going to be about. And this is an important question in various contexts, like when we try to concatenate codes and try to sort of decode them, list decoding shows up naturally. It's important in other complexity theoretic applications, etc. There is enough motivation to study list decoding. So list decoding is just a generalization of unique decoding, and we say a code script C is rho comma L list decodable if for every word W in sigma to the n, if I draw a ball of radius rho n, that is this ball centered at W of radius rho n, it can at most contain capital L code words from script C. That is what it means to say that C is rho L list decodable. So under this definition, it should be clear that unique decoding was just delta by 2 comma 1 list decodable. right? Because we just drew a ball of radius delta by 2 around W, and we said only one code word should be inside this ball. Anyways, I would like, if something is not clear, please ask me, because this is what the talk is going to be about list decoding. So there are again two questions when one is interested in list decoding, unlike in the case of unique decoding. So one is the combinatorial question. That is still what value of row, that is how large a ball can you draw around W and still keep the list size manageable. That is, let's say, even polynomial in the parameters of the code. So for unique decoding, the good thing was that as long as the distance was row by 2, the radius of the ball was row by 2, you knew that only a single code word can enter the ball. But if row exceeds delta by 2, then we would like to still keep the number of code words inside the ball to be small. And on the combinatorial front, we know that over large alphabets, it is indeed possible to do slightly better than delta by 2, which is this bound 1 minus square root 1 minus delta. This is a famous bound known as a Johnson bound. And on the flip side, we know that we cannot keep on increasing row forever. That is, if row is sort of made to be larger than 1 minus r, which is sort of the capacity, so to speak, or 1 minus r, which is the limit of list decoding in some sense, because as soon as I go to 1 minus r plus epsilon for any tiny epsilon, the list size will become super polynomial in the input parameters. And this is a simple counting argument. And of course, there is the other question, which is the algorithmic question, that fine, we will work with rows which are below this 1 minus r threshold, but can we list decode efficiently? That is within a polynomial time of the input parameters. So these are the two questions to ask in case of list decoding. So now let's see an example of a code and how it behaves with respect to unique decoding and list decoding. So one of the most famous codes, or the most well-studied codes in coding theory, are the family of Read-Solomon codes. So these are again linear codes over a finite field, let's say FQ. And the description of the code is just a set of evaluations of low degree polynomials. And okay, sorry, I thought I lost people for a while. Yeah, so the what is script-C? Script-C is just evaluating low degree polynomials at the set of evaluation points a1 to an. And another thing which is well known is that these codes are maximum distance separable codes. That is, that distance is n plus 1 minus k. And this is the best one can hope for, because this meets the singleton bound. And the reason for this is very simple, that if you take a non-zero polynomial of degree less than k, then it can at most have k minus 1 zeros. So you immediately get that the non-zero, any non-zero code word in script-C has large weight, and hence the distance of the code is also large. Anyways, so we can ask about unique decoding of Read-Solomon codes. And this is a well-studied problem. In fact, I think even Peterson did it well in the 60s, which I think predates what polynomial time was. And there are other algorithms. Berlekamp-Macy has a shift register. They have a shift register algorithm. There's Welch-Berlekamp. And they all allow for efficient decoding of Read-Solomon from less than d by 2 errors, which is the unique decoding threshold. And for list decoding, we also have some understanding of what goes on. So Suthan's algorithm lets you list decode. Initially, it lets you list decode up to 1 minus square root 2r, which is slightly shorter than the Johnson bound. Johnson bound is 1 minus square root r. And then Guruswamy Suthan sort of boosted this algorithm using multiplicities, and they went all the way up to the Johnson bound, which is 1 minus square root r. So up till now, this has been just a survey of what is known for Read-Solomon codes. And there's a big open question in this area, that can we list decode the Read-Solomon family of codes beyond the Johnson bound, which is 1 minus square root r? Can we efficiently or even combinatorially list decode? There are some results known under different settings or parameters, but nothing in general is known. There are some counterexamples, some positive results, but nothing in general. So this is a big open question. And so now, what is the question which sort of is still really important to answer, and ReadSolomon codes we don't quite know how to answer using ReadSolomon codes, is are there efficient codes which we can efficiently list decode up till the capacity of 1 minus r, up till the list decoding capacity? Because we know that beyond 1 minus r, the list size is going to grow super polynomial. So in this graph, as you can see, there is the yellow region, which is the region given by the Johnson bound, which for the ReadSolomon code, we also know how to efficiently list decode, and combinatorially, we know that you can always list decode. But the green line, which is 1 minus r, lies above this region. So the lacuna between these two regions is what we are trying to answer. And just as an aside, we can show that random codes actually are list decodable all the way up to capacity with high probability. It's not too hard to show that. But now, keeping those questions in mind, I would like to sort of come to the different thing, which are called polynomial ideal codes. And these codes will help us answer the questions we asked to some extent. So these codes were present in the work of Guruswami, Sahai, and Sudan. But I think this definition that is present in this slide is not directly from that work, but it's equivalent. So we consider any bivariate polynomial. We are going to first define what polynomial ideal codes are, then we are going to take examples so that hopefully the definitions will be clearer. So we take any bivariate polynomial exy. So it's in two variables, x and y, and with the promise that its x degree is s, and in fact it is monic in x, that is the coefficient of x power s is 1. And you further need that the set S, which is always acting as a set of evaluation points, should be such that EXAIs are all pairwise co-prime polynomials. Because when I substitute for y equal to AI, I will get a polynomial in X, and that those collection of polynomials should be pairwise co-prime. That's what the statement is saying. And what is the encoding map in case of polynomial ideal codes? Well, you take any degree. Okay, so this should have been less than k polynomials, because k is what I've been using for degree. But you take any low degree polynomial, it's not important what its degree is. And the way we find its encoding is that look at the polynomial EXA1 and just divide px by EXA1. That is, find the remainder of px when divided by EXA1. So these are all univariate polynomials, so we can even just apply Euclid's algorithm. And that remainder polynomial is the encoding function, and then you give this at all the points of evaluation as I varies from 1 to n. So if there are any questions, please interrupt me, or otherwise I'll take some examples also to make this definition clear. Okay, so I'll move on to the examples now. So let's look at ReadSolomon codes. So the ReadSolomon codes are defined actually by this bivariate ideal x minus y. And why is that the case? So the set of evaluation points stays the same as it was previously, a1 to an. So if you think about it, giving PAI, which is what usually we would do in ReadSolomon codes, it is the same as telling you the value of px mod EXAI. That is, in this case, EXAI is just x minus AI. So telling you the value of px mod x minus AI is the same as evaluating p at AI. And hence this is just an equivalent description of ReadSolomon codes. And this way we can also define a different family of codes which are called folded ReadSolomon codes, which are important for answering the questions we asked earlier. So these codes are defined by the bivariate ideal EXY given as product x minus gamma JY. So if you think about what folded ReadSolomon codes are actually doing, well, they are just at each point of evaluation AI, they are giving you the value PAI, P gamma AI, P gamma square AI, all the way up to P gamma power S minus 1 AI. And as you change the set of evaluation points, you will get a different set of values. So actually the alphabet for these codes is not FQ, but FQ to the S, because at each point of evaluation, I'm giving you S values from FQ, right? And it's sort of not difficult to convince oneself that giving the polynomial mod EXAI, or giving these set of S values PAI, P gamma AI, P gamma S minus 1 AI, they are the same, they are equivalent things. So are there any questions about this? Okay, I guess there are no questions, so I'll move on.
Siddharth, just the previous slide, that summation, that index goes from j equals 0 to s minus 1.
Oh, right. Sorry. That goes from j equal to 0 to s minus. Yeah. Yeah. Thanks. So let's look at a few more examples of codes. So defined in this language. So these are another well-studied family of codes, multiplicity codes. So here the bivariate ideal has a very clean form. EXY is just x minus y power s. And the rationale behind this is that in multiplicity codes, we would usually give the evaluation at a point, its derivative, its double derivative, and s minus 1 derivatives. And that is the same as telling you what is px mod x minus ai to the power s. I mean, the easiest way to see this is let's just keep ai to be 0. Then telling you px mod x power s is like telling you the degree s minus 1 to degree 0 coefficients of x in px. And that information is
expansion, right? Isn't it just Taylor expansion?
Hello?
Isn't that just Taylor expansion? Which
Yeah, that's just Taylor expansion. That's right. It's exactly the same. There is no difference. And then there are yet other family of codes, another family of codes that were studied before, which were called additive folded ReadSolomon codes, where the ideal is instead of is defined in such a way that instead of giving you evaluations of p at ai, gamma square ai, which was the case with folded ReadSolomon, you give the evaluations at p of ai plus beta, so on up till p of ai plus s minus 1 beta. So the set of points ai plus beta, ai plus s minus 1 beta are in an arithmetic progression. So these codes are called additive folded ReadSolomon codes. And anyways, these are just examples of codes which can be captured in this language of polynomial ideal codes. But of course, polynomial ideal code need not have this nice factorization into linear factors. The bivariate polynomial EXY could be an irreducible. But these are just some examples. And sort of in our work, we define a common generalization of all these examples that we saw earlier. And it sort of very nicely unifies all the results we knew about list decoding capacity prior to this work. And these are what we called affine folded ReadSolomon codes. So here EXY is defined as x minus LIY as I goes from 0 to s minus 1. And Ly is just an affine form in y. So it is alpha y plus beta, where alpha y are members of FQ. And Liy is nothing but the iteration of the affine form L times. So notice that if Ly is an affine form, then L square y is also an affine form. That is, its degree in y will continue to remain 1. And it should be fairly clear that the codes we studied prior to this are all instances of affine folded ReadSolomon codes. For instance, here in case of folded ReadSolomon codes, the linear form Ly is nothing but just gamma y. And in case of multiplicity codes, Ly is just identity, Ly is just y. And in case of additive FRS, Ly is y plus beta. Because if you apply L twice, then you'll get y plus 2 beta and so on. So this is a common generalization, and we'll see that later we are able to prove results which were known for these specific cases even in case of affine folded ReadSolomon codes. So what are the results in our work? So the first result is that we show polynomial ideal codes actually can be efficiently list decoded up to the Johnson bound. In some sense, this was stated in the work of Guruswamy, Sai, and Sudhan, but we sort of flesh out the details, and there are a few steps which were missing, which we fill. And the second result that we prove in this work is showing that affine FRS codes, the ones that we just defined, they under mild assumptions on the form Ly and set of evaluation points, etc., they are able to achieve less decoding capacity. So the reason why this is sort of nice is that it captures results which were known for specific families of codes, but in an ad hoc manner without sort of any principled approach in the proofs. So, like, we knew that folded ReadSolomon codes achieve less decoding capacity, multiplicity codes achieve less decoding capacity, then additive FRS codes by an observation of Swastik, they also achieve less decoding capacity. So, all these results sort of now get tied up into a single result saying that affine folded ReadSolomon codes achieve less decoding capacity. And the main idea behind the proof is sort of looking at Guruswami Wang's approach. So Guruswami Wang had a different way of proving that these codes achieve less decoding capacity using a linear algebraic framework. So we abstract their approach and in terms of linear operator codes, and we sort of show a very intimate connection between polynomial ideal codes and codes which are defined using some nice class of linear operators. And that's it. And that's all. I think I'll overshoot my time beyond this. I might have already completed. Yeah, I think I'm just on time.
Okay, thank you. So, any questions? So, if there are no more questions, okay, let's thank Siddharth again. So, I think now we break for lunch.
Piyush, can I ask you a question?